So guys, do you see my screen? Okay, probably you can see my screen, right?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir, it is visible.
Okay. Now this is our new topics. Actually, this is our last topic also, channel coding. So channel coding. So we have already covered a small portion of source coding. Actually, source coding is not actually that much in our syllabus. That's why channel coding is a little bit longer syllabus. So what happened in source coding? What we did actually in source coding? Remember what we try to do in the source coding? What is the purpose of source coding? The purpose of the source coding is to remove the redundancy. What is the redundant bit? Means the bits which actually occurs very often. Then, for example, in our JPG or MPG still picture or movie picture, we compress it actually, right? Before transmitting to reduce the data pack size. That actually we do in the source coding. Okay, so in the source coding, we actually discuss only one topic, which is actually Hoffman code. Other stuff we didn't actually discuss there. Now, in channel coding, what we do in channel coding? Channel coding actually, for example, when you the purpose of channel coding actually, the reason of channel coding is we are assuming that our channel is noisy. For example, you have a your message signal. For example, you have a message signal. Okay, then this message signal is converted to our digital, pure digital. For example, ones and zeros. It was an audio signal, whatever, something like that. Analog signal. We converted a stream of digital signal, right? So probably then we actually goes through our multiplexing technique that we actually studied previously. ASK, MSK, PSK, blah blah blah. Then for all this, after all this process, we actually transmit through the channel. Imagine this is actually our channel. Now we are assuming that okay, when we will be transmitting our information through the channel, there is a chance that this information will be lost or noise will be added in the channel. Means when we will be in the reverse back, when we will try to decode the information, will actually this will be wrong information. For example, 0 1. You see, this is not the same information. Means actually there will be error in the system. To detect that error, we actually add some extra bits here so that we can check that bits here so that we can detect the error and we can correct the error. Means actually everything is based on this channel. That's why it's called channel coding, because we are assuming that noise will be added in the channel and our signal will be lost. That's why as a precaution we will add some extra bit here or extra information here. That information will give us that whether our information which we receive, whether it is a good one or no, right, correct one or not. Or in case we can detect it, we can actually, in digital communication detection, if you can detect it, it's easy to correct it, right? Because it's nothing but 0 and 1, like 2 bit. If I know that this bit is wrongly detected, then alternative will be only 0 or 0 will be 1. That's the easiest part, right? If we can detect it, we can correct it. So in channel coding, what we do, we actually add redundancy. What is adding of redundancy? For example, I have 0 1 0 1. Just imagine. So I will, for example, very commonly ways transmit it in few times. Transmit 0 3 times, 0 0 0. It's not a code, individual code. Transmit 0 3 times, transmit 1 3 times, transmit 0 3. See, just to so there, of course, there is a trade-off in between this. So the type of this channel coding or error correction or control code, this one, because we try to control our error in the channel because of this, and we detect it here. That's why it's also called error correction or error control mechanism. Channel coding is also called error correction or controlling mechanism. There are two ways. One is the error detection and retransmission. Very like simplest way. what happens in a simplest way. For example, you have a transmitter, you are sending a packet 1, receiver receive that packet. If it receives correctly, it will send an acknowledgement, okay, I received it correctly. If it's the transmitter will send the next packet. When the receiver receives the next packet, or for example, in this case, it didn't receive the next packet correctly, it will send a negative acknowledgement, means actually send it again. Package 2, you see, package 2 was here, but it has a negative acknowledgement, so you have to send it again. Once it that receiver send the acknowledgement, means you do not have to send it again, right? So then packet 3 will be transmitted. Now there is no acknowledgement here, means the transmitter knows, okay, there I didn't receive any acknowledgement, means automatically I have to send the packet again. That's why he transmits it again, because he did not, this acknowledgement, both positive and negative, both acknowledgement is missing either way, right? So he actually guessing that, okay, the packet did not arrive correctly. This is actually, probably you already know it, this is called automatic repeat request mechanism. There is a request for repeating the transmission. It's actually a so this kind of system is little bit laggish. It's actually if your system is delay sensitive, you can use this kind of mechanism, this mechanism. Okay. So the alternative is forward error correction mechanism. What we do here, we add a parity bit in our message. So two-way. So this is actually delay sensitive mechanism. This is a delay insensitive mechanism. Means actually, sorry, I beg your pardon. This is delay insensitive. If you have a delay in your system, you can actually you will use it. But if you do not care about delay, then you will use retransmission, because you see retransmission takes time. For example, you're transmitting something, for example, live sports is happening. There is no way that you will wait, right? It's happening live. So your information has to be transmitted like on the spot. Okay, so this is delay insensitive. This is actually delay sensitive. Means FCC is will be forward error correction mechanism will be used in a mechanism, while delay is actually very vital. If you do delay, information can be distorted. Okay, so here we say how this happens. It happens by adding a parity bit. Okay, we'll discuss about what is a parity bit. Means the code word, actually our final word, final combination of 1s and 0 is dependent on the our original data plus a parity bit. So probably our data is 0 1 0 1 0 combination, then you add some parity bit. Okay, based on this parity, this will be our total code word. That's why one we called it code word. The one we actually receive here we actually receive code word. Okay, so because this is very popular, forward error correction is actually two types. One is the block codes, and another one is the convolution code. Convolution code, actually I have already give you introduction of convolution. Probably I will add a few more lectures in that convolution code. So from its name itself, okay, what is a block code and what is a convolution? Block codes is actually a block, nothing but a block. So what is a block code? Is a block. Means, for example, you have 0 1 0, like whatever stream of your data, you will actually give it as input in this block, then like 0 1 0 0 1, whatever some other information, or this information will be processed. In our cases, in parity bit will be added here, blah blah blah. Then the whole block will be out, like equivalent to this there will be another block of information. Okay, that is called block code. But in convolution code, this do not happen. In convolution code, like whatever data comes, 0 1 0 0 1, for example, these data, immediately 1 converts, then 0 comes, immediately 0 comes, then 0. That's the equivalent 0 equivalent of 1 it creates as a convolution code, like on spot, based on our convolution algorithm. Okay, so you see in block code you have to wait for a block. Okay, this is your block of information that goes, some process happens, then same like equivalent block of code word comes out. But in convolution code they are individual, this data bits are individual. For their equivalent convolution code will be generated. Understand? Like it's instance, but it's not instance. You have to wait to generate the complete block code. Okay, so convolution code, another kind of codes are turbo code. Turbo code is not actually in our syllabus, so I have actually discussed convolution code in the uploaded lecture. Right? So today actually I will more focus on the block codes. So block codes could be this example could be this. It can be a linear block code, and one of the example is a Hamming codes. It could be cyclic, low density parity check code (LDPC), and Red Solomon and blah blah blah. So they are actually probably in our syllabus. So we are actually in this today's lecture we are more will be concentrated to the block codes. Okay, very common is the Hamming codes. So I think if you have the example of the Hamming codes, then actually you will have the idea of whole like blocking of stuff. Okay, so what is a Hamming code? Probably I'm not sure. Probably you studied. Have you studied this in your digital electronics? How to generate Hamming codes by digital circuitry? By chance?
No, sir.
Okay, so this Hamming code is also covered in digital electronics actually, because this can be generated. But actually, see here we are actually using some kind of equation. They can be converted to the equivalent digital your AND gate, OR gate, XOR gate, combination of that, right? So they can probably Hamming code actually also be covered in digital electronics also. Okay, anyway, so Hamming code. What is a Hamming code? To detect and correct error. So Hamming code can detect. You see there are two stuff always. Detect and correct. Now, not all the block codes can like all the block codes. Of course, you have this is the fundamental capability that you can detect an error. It's not that if you can detect, you can correct it. It's not. Probably some mechanism you can detect there is an error in the message, but you do not, or you cannot correct it. We'll see in by example. Okay, so detection is very fundamental capabilities, but correction is not. Like it's like advanced capabilities. Okay, so Hamming code can do both, detect and correct. So and what it do, he actually use a parity. Probably this is very familiar parity. This also covered in electronics, even parity, odd parity. Probably in your second year, we'll see now how a Hamming code is represented. It's represented by an N and K matrix or N and K notation. N is the total number of bits and K is the message bit. So what will be the P? Parity bit is the rest of the bits are parity bit, isn't it? For example, just giving an example, N is the total bit. So total bit is always higher, 7, and you have message bit is 4. So how many parity bits? Actually 3. Our original message was 4 bit. So you add 3 more, so the total bits become 7. Right? We'll see through our example. Now, to satisfy our Hamming code, this condition must fulfill. 2 to the power p plus k plus 1. So what is this p? This is the nothing but the parity. P is the parity bit. Okay, so let's see an example. Actually, in this lecture, I will try to avoid more like giving you theory than try to give an example. Like once you have an example, you can easily goes back and can find what is it means or what the theory says. Okay, so it's more easily understandable. Okay, so here is given that for a message, K is the message. You see here, K is the message. K is a message bit. Okay, so it's given that K equal to 4 means 4 bit is a message bit. If K is a 4, then our this becomes 2 to the power P becomes P plus 4 plus 1, which is K, P plus 5. Okay, now we will find, we'll do for P equal to 1. We do not know. We do not know the value of P here, right? Or here. We do not know what is the value of P. Imagine P is 1. So 2 to the power 1, 2 to the power 1 is greater than or equal to, what has happened? is 1 plus 5, 1 plus 5, it will be 6. So it's 6. So is 2 is greater than 6? No. So this condition do not fulfill. Okay, so 2 to the power 2 when p equal to 2. So 2 to the power 2 is 4. 4 is greater than 7? No. Okay. So 2 to the power 3. 2 to the power 3 means p equal to 3. 3 plus 5 equal to 8. So 2 to the power 3 when p equal to 3. 2 to the power 8. Is it 1? Yeah. 2 to the power 3 is 8. So this condition satisfied. So at what p this condition satisfies? P equal to 3. Means if I have a message bit 4, I should have a parity bit 3. Got it, guys? Means actually, if I have a message bit 4, I should have a parity bit 3, which makes my total code word 7. Means it's actually 7 for code. Got it, guys?
Yes, sir.
I'm trying to satisfy this condition. At what p this condition satisfies? Means actually, if you at any moment if you give me a message bit, I will try to find how many parity is required for this message bit. That's all actually. So I find, okay, if my k equal to 4, my formula says you need at least 3 parity bit in your message, so that it becomes 7 bit. Okay, so that's actually my conclusion. Okay, for p equal to 3, the k equal to will be the 4 bit. Okay. Now, where will be the position of this parity bit? Position of this parity bit is, I have how many? 7. You see, I have 7. I have a 4 message bit, and among them 3 will be the parity bit. So total bit becomes 7. So how they will be organized? They will be organized like this is like positioning. 1, 2, 3, 4, 5, 6. I need 7 bit. In the 7 bit, so where will be the position? This is the this describes the position. Okay, position 1, P1 means parity bit 1 will be 2 to the power 0. 0 is 1. So at 1 position will be P1. So P2, parity bit 2 will be 2 to the power 1 at 2. So this is the second position. P3 will be 2 to the power 2 is 4. So at fourth position will be the P. You see, P1, P2, and P3. The rest of the bits will be the data bit, our data bits or message bits. So D3, D5, D6, D7. So total becomes the 7. You see here I have 1, 2, 3, 4 message bit and 3 parity bits, which makes me total 7 like code word. Got it, guys? Okay. Now the value of parity bit from the message bit. How you find the value of parity bit from the message bit? You always have a message bit, but you do not know the parity bit. That's actually the idea. And I will give you a like how many? We have 4. For example, you have we have 4 message bit, right? So this 4 message bit can be 1, 1, 0, 1, for example. Now you have to generate extra 3 parity bit based on this message bit. Okay, that's actually we are trying to see here. Okay, means actually what we know the position of the parity bit, right? It will be here, it will be here, it will be here, right? Data bits we already know it. What will be the data bit, but we don't know what is the. Now by this we know the position of the parity bit. So we need to know extra what should be its value. Okay, so for example P1, what is the value of P1? P1, check 1 bit and skip 1 bit. That actually I draw here. You see, I draw the same one. This is actually the same thing here, right? So check 1 bit and skip 1 bit. So you see, check 1 bit, skip 1 bit, check 1 bit, skip 1 bit, check 1 bit, skip 1 bit, check 1 bit. So P1, okay, P is the check 1. So skip this part. Then this is the check. So it's a check, check, check. Who are the check? D3, D5, and D7. So D3, D5, and this they will be the XOR. So if I do the XOR, then I will get the P1, like value of the D. They are data bit or message bit. If I know the message bit, I can easily generate the P1. Same thing for P2. For P2, what happens? Check 2 bit, skip 2 bit. That actually for P2, check 2 bit, skip 2 bit, check 2 bit. So if you check 2 bit, who comes? D3 comes, is skipping, so you don't have to consider it. Then D6, D7. You see D3, D6, and they will be XORed. they will be XOR. You can find the P2. Okay. For P4, same thing. Check 4-bit, skip 4-bit. Okay. So check 4-bit for P4. This is the check 4-bit. Within check 4-bit, because you see there is nothing here in this message here, right? There, if it is a long bit, then it could have this one. Okay. Okay. How to move it? So in this check bit, I find D5, D6, and D7. That's actually right. D5, D6, and D7. They will be our XOR. Up to this, is it understandable, guys? How we find P2, P1, P2, and P4, the parity bit value, because you know these values, you can find the parity bit values. Okay, let's see example. Here is an example. So 1, 2, 3, 4, 5. So k equal to 5 message bit is there. So our condition was 2 to the power p k plus k equal to 1. Okay, so k is 5, so p plus 6. You see 5 plus 1 is 6. That's why it's p plus 6. Okay, let's check at what p this condition satisfies. Okay, 2 to the power 1, it cannot satisfy. 2 to the power 2, it cannot satisfy. 2 to the power 3, it cannot satisfy. 2 to p equal to 4. Okay, what will happen? It's 16, eh? Is greater than 10. This satisfies. Means actually we find that p equal to 4. At p equal to 4 value, this satisfies. So I know p equal to 4. Our message bit was, you see, 1, 2. This is 5 bit. Eh? So this is actually our 5 bit message bit. What will be the n? N is the summation of both. N is nothing but n equal to, the total code word is nothing but the parity bit plus your message bit, which is 5 plus 4 equal to 9 bit. You have a 9 bit total code word. So this is actually nothing but a 9, 5. 9 is the total, 5 is the message. 5 is the message. Eh? It's actually 5, 9, 5 Hamming code. Now, if it's a 9, 5 Hamming code, I will have 9 total. Eh? So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9. Among them is so what? Do the same thing. Why will be the p? So p1 will be 2 to the power 0 at 1 p1. P2 will be 2 to the power 1 is at 2 at 2. So you have at 2. P2 to the 3 at 4 and at 8 you have parity bit. Rest of them 5 will be the data bit. 1, 2, 3, 4, 5. So 5 will be your data bit. They are actually this data bit. This data bit. Okay. Now we will find the P1. What is the value of P1? Value of P1. Eh? What was the formula for P1? Guys, remember P1? Check, skip, check, skip, check, skip, check, skip, check. You see, check means D3, D5, D7, D9. D3, D5, D7, D9. So they will be XORed. Understand? Guys? Okay. Now for P2. For P2, what is happening with for P2? P2, eh? So now 2. Check 2, skip 2. Check 2, skip 2. So who have here? D3, D6, D7. D3, D6, D7. Right? For P4. Eh? Same thing. 4, 4. 1, 2, 3, 4. So skip. Where is? Check and skip. So D4. 5, 1, 1, 2, 3, 4. Check 4. There is no 4 here actually. There is no extra bit here. So okay. So we have 5, 6, 7. 5, 6, 7. For D9 on the only P8 only 1 remains. Like it was like check 8. So we do not have 8. So We have only. So guys, got it, guys? So do you understand P1, P2, P4, and P8? So now we will try to figure it out. P so D3, D5, D7, D9. D3. So let us put the values. Then easily we can understand. So let me erase all these values. So what was our data? Our data message bit was 01101 01101. Okay. So our message data was D. 01101. This is actually message data. So we are writing here D3, D5 is 0. You see, D5 is 0. D7 is 1, and D9 is 0. D9 is 0. You see. So here this is XOR. What is XOR? Remember anyone? Like 0 0 0 1 1 0 1 1. If I do XOR, what will happen to our truth table? Remember 0 0 0 0 1 1 1 0 1 1 and 0. If they are similar, it's 0. Otherwise, it's 1. So you see 1 and 1 is 0. So 1 1 0 0 1 1. So 0 1 1 1 0 0 0 0. So and P8 is automatically 0. So now I can replace them. What is P8? P8 is 0. P8 is 0. What is P4 is 0. P4 is 0. P2 is 1. P2 is 1. And P1 is 0. P1 is 0. You see, this is our total code word. 0 0 1 1 0 0 1 1 0. This is actually our total code word. This will be transmitted. Got it, guys? No? It's easy, eh? Are you following?
Yes, sir.
Okay. So Hamming code is easy because it's only adding the parity. Okay. Now, how to detect it? Because we know Hamming code can also make. For example, we are generating this way. This is the way we're generating the code. Now, how to detect an error? So here is an example. A received Hamming code is 1 2 3 4 5 6 is 7-bit code. It's actually. I'm not giving you theory, guys. Okay, I'm giving an example. If you understand example, you understand the theory also. Okay, so this is a 7-bit code. So you see 1 2 3 4 5 6 7. So here we have the message bit. So now from the okay, we know where will be the P. This is actually Hamming code. 7-bit means actually the data and parity is there. It's nothing but the data plus parity. Because it's a receive code. Okay, means it contains data, it contains parity. So where will be our parity position? We know from the previous. So 1 2 and 4. So at 1 2 and at 4th position will be our parity, and others are. So here you see this 1 1 1 0 1 0 1. That is our total code. Means actually we know the position of the parities, we know the position of the datas. Okay. Okay. Now we do the previous one. P. What is the P? Sorry, P1, P2, and P4. Same formula we did it before. Okay. So 1 1 P1. So P1 is dependent on the data 1. So 1 1 0 0 1, like 1 1 0, because they are XOR. 0 1 1 0 1 1. Is it same as P1? Yeah, it's same as P1. P1 was 1. So it's okay. For P2, P2 is 1 1 1 0 0 1 1. P2, is it P2? No, it's not same as P2. You see, it's not same as P2 because means actually this is the wrong parity. So P4. So 1 1 0 0 1 1 1. Is it same as P4? P4 is actually is giving 0. Means actually you see it's not same. Means it's not same. So this is actually an erroneous bit. Means actually that so what we have, we find P4, P2 and P1, which is actually like 1 1 0. 1 1 0 is 6, isn't it, in the binary, guys? 4 2 6. So actually 6th bit is in error. That's why our calculation do not match up. So we can find it that okay, 6 bit will be in error. So 6 bit means which one? This one actually. 6 bit is actually in error. So 6 bit is actually 1. It was 1. This guy was in error. So this is called error syndrome. We'll actually write 6 bit. We don't care about the others one. This is actually our original receive bit, the Hamming bit, which is actually this one. This one. You receive this one. After receiving, you do this calculation, and you detect that okay, this is actually, this should be the parity code, and based on the parity code, we find that error is actually, we already know that there is an error happening of because of these 2 bit got mismatched, and from the parity bit we know the position is actually the 6th bit. So we find the error syndrome and the receive code. So the corrected data will be error syndrome and the receive are XORed. So you see 0 1 0 1 is 1 1 1 0 0 1 1 0 0 0 0 1 1 0 0 0 0 1 1. You see every data remains same except this altered, because it was 1 which is actually not the correct bit, so he changed it, so it becomes 0. Now it becomes the correct one. So we can detect it, we can correct it. Got it, guys? Guys, question? You see, by
Sir, I have a question. Is the syndrome always expressed in binary? Is the syndrome
error syndrome?
Yes, yes.
Here everything is binary, because our data is transmitted data is binary. I'm not talking about, it's not like 101 million. It's we are transmitting digital. It's actually
No,
this one.
sir.
Whatever.
Okay, that is not what I meant. We had a question like, which row does the syndrome 3210 belong to? So I was really confused. Is 3210 a syndrome pattern or something?
Which
I thought it was always expressed in binary.
I didn't get the question. Can you repeat it, please?
The syndrome
Mm-hmm.
the syndrome pattern 3210, which row does it belong to in the syndrome table?
Okay, here our parity gives the hint that the 6th bit is actually in error. So 6 bits actually, where is our 6th bit? 1 2 3 4 5 6. This is a 6th bit. So that's this, we know this bit actually is in error. Of course, we as a digital, we could actually, we do not need to do this process, because we know this is in error means I can alter it, it will be corrected. But how the circuitry will do, it will do the XOR operation with the received data. Then you automatically, you see all the data, this one and this one, this remains same except this altered. Make sense?
Yes, sir.
Okay, probably you're not happy. I could not I don't know whether I understand your question.
No, sir, it's not a problem.
Again, please repeat your question again then.
Sir, the syndrome pattern was 3210. It wasn't even
Where is
binary. It was
3210? What do you mean by 3210?
Sir, it was a question in our lab quiz. If the syndrome pattern is 3210, which row of the syndrome table does it belong to?
3210.
10, yes.
3210.
Yes.
This way?
Yes.
Because syndrome we always get in we cannot get 3, these 3. Or
Yes,
it
right.
can be positioning of, I don't know. Eh, Probably
Okay, sir.
you can forward me the question probably in our Google class. Probably I will try to have a look. Okay.
Okay, thank you,
Okay.
sir.
Okay. Okay. So you see, we can detect and we can correct it. Once we can detect, it's easy to correct it actually. Okay. Okay. So uh, okay, there is a small portion, even and odd parity check. Even and odd parity check. We can actually, this is actually, for example, this is very easily understood in your electronics. So, for example, let's say 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Now this is actually, for example, they are actually stream of data our, okay, this is actually our stream of data. Now I like to transfer or convert it as a even parity. What I would do, for example, I will try to make this one even. Okay, so how I will make it even? This is odd, so I will make 0 if it's even. It's even parity. So it's odd, so I will make add 1. So 1 here, I will make 1 here. It's already even, I will make 0. So it's already odd, so I'll make 1. It's already even, so I'll make 0. It's already even, I will make 0. So it's odd, I will make. So this will be our actually our, so this will be individual total code. You see here, they are always in even. There is always an even code. So it's actually even parity. This is how we make it even parity, or odd parity is just opposite one. Try to make this number of ones as an odd number. So this is how we actually make a even and odd parity. Even and odd parity, it actually can detect, it cannot correct your error in the system, like very poor kind of error detection system, or error is cannot correct. So it's actually very poor error detection system. Okay, so we'll actually in a previous, there is an example. Next we'll actually see that how this even and odd parity can do. Okay. Okay, so continuation of your block code for parity check. Do I have to go through it? Let's see. Now we already have discussed it. Okay, what I actually try to see, we actually give you an example. This is actually the theory, how the how this block code, how this block code theory is actually expanded. Okay, we are already discussed about like the code word, how this code word expressed. We don't have to go through this theory. It's actually same thing. Now given even parity, receipt block code, blah blah blah, check. Okay, there is also a small example is given here. Okay, so this is an 8-7 even parity code. 8-7 means what? 7 will be the total data and one extra parity check, make it 8 code words. You see, 1 2 3 4 5 6 7 8. It's actually the example for this odd or even parity. This one is actually an example for this one. Okay, so what it do? So we know nk. So we have the ak is 7. So p parity is 1. This one will be even or odd. Okay, the checksum is nothing but the nothing but the XOR of the whole data. So you see 1, this is 1, 1 0 0 1 1. So 1 1 0 0 1 1 0 1 1 0. So if you do this XOR, you have a 1. Now what is that? If a is equal to 0, even parity coded with correct received. This is actually is given our even parity, means actually it's supposed to be 0. If it's 0, then this was a good code word because it's opposite one. So if s equal to 1, odd parity code word. If it's not, so our checksum will always be 0. If we use an even parity, our checksum will always be 1. If it's odd, if it's opposite, means the signal is in error. We do not know actually here. For example, parity, even or odd parity cannot tell us where is the error. it can tell us there is an error here. But at what position, it cannot say. It cannot tell me at which position the error happens. Which bit is in error? Which bit is in error? It cannot give us because it's a single parity check code. Odd and even parity check code is a single parity check code. It cannot correct it because it do not know at which position. It knows there is an error happen, but it do not know. How we can like overcome, or we can make the single parity smart one. This is not a smart one, so we can convert this single parity check code with a smart one by using a product code. Means actually we use two single parity. Here is an example given here. You see there is a data bit 1 1. It's like arbitrary code. Okay, so it's a even parity. It's an even parity. Even parity means what? You see 1 1 1. It's odd, so I add an extra 1 to make it even, right? So this is actually this one is my row parity. I add an extra 1. So 0 1 1. So 1 1 is already even, so I add 0 to keep it even. So 1, so I add extra 1 to make it even. So 0 0 0 0, so I make it 0. 1 1 1 3, so I make it as a 4 even. 1 0 1, so it's already even. I add a 0 1. Now I add, this is my row parity. Row parity. I will do the same thing in my column parity here. You see, it's 1 1 1 1. So it's actually 4. So I will add 0 to keep it even. 1 1 1 3. So I add 1, so make it even. 1 1 2. So I add 0 to keep it even. 1 1. So 2, I add 0 to keep it even. Okay. Now you see 1 2 3 and 1 is here. There are what? Odd. So I add extra 1 to keep them whole even. So this is called overall parity. You see, just by make a matrix, it's still a block code. What do you do? This whole block, you see this whole block of information, they will be blocked together, adding parity, and then will transmit it. That's why they are called block code. They do not work as a instantaneous. Okay, so I need a row parity, I need a column parity and overall parity to make it a product code, or like two single parity. You see, it's a single parity. So here is a single parity, here is a single parity, here is another single parity. It's called double single parity. To make it as a matrix, so that I can now here it can it detect an error? For example, I write it here 1. This 0 is not 0. Somehow it altered. It becomes 1. What will happen? The parity, this 0 will tell us this is the wrong one, isn't it? And this is also tell us this is the wrong one. So where is the intersection? The intersection is here. So if you go the wrong one, if you do the wrong one, here is the intersection. Means actually here is the location of the wrong bit. If I know the location of the wrong bit, I just altered that bit. My code will be perfect. The problem is that this block code, like product code, it can detect only one position change of one error, 1 bit error. If 2 bit error happens, it cannot detect. For example, simultaneously this also becomes 1. Then you see this was 1, this was 1 1 is even, so automatically this is 0. So it cannot detect this error, isn't it? Previously there was only 1 was here, which is actually odd, so this 0 do not goes there. It's supposed to be 1. But when it becomes 1, there is 2 1 here, means it's already even, so 0 is still okay. Means if 2 bits changes, this product code cannot detect that 2 changes. So this is actually a 7/6 code word. So our product was 5/4 and 7/6, which we have actually 34 code word, among them 24 actually bit, and rest 11 is actually our code word, our parity. You see, 1 2 3 4 5 6 7 8 9 10 11. So 11 is actually our code. So it can detect only one bit. It cannot, if 2-bit altered, it cannot do it. It thinks that the parity is okay. Understand, guys? Okay. Okay. So linear block code. Okay. What is a we so far we talked about block code. Okay. So this is a new term, linear block code. A block code is says to be linear code if its code word is sum of any two code word. Means linear operation happens like if you receive, for example, if this is the block code and there is another block code, if you add them, oh sorry, this is not a XOR, I make it. So if you add them and if you receive another code word, this will also be a like this is if this this is the summation of these two, then they are linearly added. Means actually this is a linear block code. Means this is a block code, by adding with another independent block code, you received you generated another block code. If they are the sum of equal, then this is called a linear block code. Okay. Okay, just see an example. So these are the properties. We will actually check with these properties. So all 0 words, blah, 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 is always a code word. Means 0 is actually still a code word. Given any 3 coders, CP such that, okay, this condition fulfills, which is actually this one. And this is D. This is Hamming distance D. Okay, what is Hamming distance? Probably if you see my previous record, like convolution, you probably already know Hamming distance. For example, you transmitted 0 1 0 0 1 and you receive 0 0 1 0 1. How many changes happens? Here the changes happen. This is transmitted, this is received. So 1 bit changes, this is transmitted, this is 2 bit changes. Means actually this is the Hamming distance. 2 Hamming distance happens. And what is this W? W is nothing but the weight. So linear block code will satisfy these 3 conditions. Instead of going through these 3, why not let's discuss or see an example. It will be easier for you to understand. Okay. So the series of Hamming code, among this I will actually choose 2 Hamming code. C1. C0 is 0. C0 is nothing but the like 0. How many? 1 2 3 4 5 6 7. So 2 3 4 5 6 7. This is Hamming linear block code is saying the C0 is also a code. Means 0 0 is a code. This is our first condition or first property, that this is also a code. Means actually this is also a code. Okay, now here C1 is this one and C10 is this one. Do you see any Hamming code here? Where is the code and where is the data? You see here, see, you see this is 1. That's why I'm saying C1. This is 10. 8 to 10. That's why it's become 10. And this part is really the parity. Parity is added in the system. Okay. What is the weight? Weight is how many ones? How many ones here? 3. How many ones here? 1, 2, 3, 4, 4. So the weight for C1 is 3. The weight for C10 is 4. So if I add them 0 1 1 0 0 0 0 1, oh of course this is actually XOR. XOR operation means 1 1 will be like 1 1 will be 0, 1 1 will be 0. What is this code actually? You see C11. This is nothing but 11. You see 8 10 1 11. What is the weight here? This is the weight also 3. So I can say C11 is nothing but C1 plus C10, which is actually this condition. This condition. C11 is nothing but C1 and C10. Which we are saying that summation of 2 individual block code will create another independent block code. Summation of 2 C1 and C2, C10 independent block code will create C11 as an independent block code. Okay. So what is the distance between C1 and C10? C1 and C10. Let me delete, then it will be easier for you to understand. Okay, so C1 and C2. Let's see. These changes. Here the changes happen. Here the changes happen. So how many distance happen? Distance is 3. What is the weight for the C11? Is 3. We are saying that distance of C1 and C10 will be the weight of the C11, which is actually, here we can say what is the this formula, this checksum, right? So the distance between two individual code is actually the weight of the resultant code, and the last one is the minimum distance of the code is d minimized is the minimum weight. What is the d minimized? 3. We have seen the d minimized is 3, and what is the minimum weight here? You see, minimum weight is 3. So the condition fulfills. Here we say, when if you complete the whole code, we will see that C15 will be all 1, right? 1 2 3 4 5 6. So the weight will be 7. 1 2 3 4 5 6 7. How many ones? 7 ones. So maximum weight is 7. But except this code, all other codes will either have a 3 or 4. What is the minimum? Minimum is the 3. So minimum weight is actually equivalent to the minimum distance. Minimum distance is 3. So means this condition also fulfills. Means actually, if I give you this example, then you can prove, okay, this is a linear block code. Can you? If I give you any series of code, can you prove that whether this is a linear block code? Yes. Isn't it, guys? But you will just try to prove these three points. This will satisfy, this will satisfy, this will satisfy. It's very easy stuff, right, guys? Okay, is there anything else here? Guys, question? Either you didn't understand or you understood everything. These things are easy, guys? I am not actually giving you formulas like theory. Theory is easy. For example, instead of going through this stuff, all these properties, if I do this math, it's easier to understand, right? Okay, this property is satisfied. Okay, guys. So, among our syllabus, let's see if I go back. So convolution code will be in the is already in your uploaded. So we covered our hemming, and we covered the linear block code. So they remains. Okay, cyclic LDPC. Actually, LDPC actually is in our syllabus. I have to check. Cyclic is there. 1 or 2 topics, probably more. Okay, so one more topic. Let's see if something remains. Okay, so generation metric for linear code. Actually, this generation metric is very popular term. In our convolution code, I also did the same thing. I use a generation matrix. Generation matrix is a quantity. Like if you know an algorithm, but if you know this quantity, I can easily generate that same code. Means actually, you see, I can at any moment create a code word if I know the generation matrix. Generation matrix will always be like it's a given term. For a specific operation, it's a given terminology. So C is the code word. This is the information. So you have a information, basic information. You know the generation matrix is fixed for a particular operation. Generation matrix is fixed. Easily you can generate a code word. That's actually it's saying that at any moment, if you have your info, you know the generation matrix, then easily you can generate the corresponding code word. Okay, here it's saying the in generation matrix of nk linear code, k is the rows and n are the columns.
Merci.
Hello,
Enoi adodo man atimiliri beman.
who is talking? What's happened? Okay, so probably someone was talking. In generation matrix, we say k will be the rows, n will be the columns. Give an example. So generation matrix of 7 4 code is given by g. G is actually is given here. This is a identity matrix and p is the parity. This will in your math, for example, if I give you a math, this generation matrix will always be given. Generation matrix has two parts. One is the identity matrix part, another is the parity matrix part. Okay, so like we do not have to bother about how they are generated. It's generated somehow. We don't care. Okay, of course, this is actually 1 1 2 3 4. Okay, now see this example. Our I is given, information matrix is given 1 2 3 4 4 bit information matrix with 4 7 4 is given generation matrix. Okay, this is generation matrix is given, message is given. We are trying to generate a code word. So we know from the formula that okay, code word is nothing but the I is given, and generation matrix is also given. So generate a code word. Generate a code word. So this is a matrix. What we would do, you see here, this is a 1 2 3 4. So this is a 4 into 1 matrix, and this is actually 1 2 3 4 5 6 7 4 into 7 into 4 matrix. So this is actually 4 1 into 4 matrix, and this is actually 4 into 7 matrix. This one, this one. So what we do with this whole code word, you will multiply with this whole rows. So 1 into 1 into 1, like 1 into 1, 1 into 0, 1 into 0, 1 into 1 into 0, 1 into 0, this 0 into 0, 0 into 0. So we have 1. We have this 1. Same thing again, same again the same one, same code word will be multiplied with the second one. So 1 into 0, 1 into 1, 1 into 0, 0 into 0, give it to, like you see, this one and second one is 1, so that's why it's 1. Again it will be multiplied by this row, this row, this row, this row, and this row. They will be XOR plus. Actually they will be XOR, XOR. So we will actually have this. So this is actually our code word. Means if I give you a I 1 1 1 0 1 1 1 0, you have to have a generation matrix where you add this parity 1 0 0. By this generation matrix you actually can add this parity where you have a 1 1 1 0 code information plus a parity code is automatically added because of your generation matrix, because of this code. Okay, so we know how we generate by using a generation matrix, how we use code in the block code. Okay. Okay, so we actually covered mostly of our this syllabus. The other part remains. Inshallah, in the next classes I will discuss about this too. This probably 2 topics will be remaining. 2 topics will be remaining, probably LDPC, and I'm not sure one of this cyclic code or other code. Actually 2 topics will be covered from here, and I have already covered convolution code. 1 or 2 lectures can be added here. Okay guys, question.